Hi guys, in this video I would like to talk about the problem of using LLMs and AI for solving mathematical problems and proven theorems. Because I think it is a kind of reasonable question. Why do we have all this complex and difficult to use software? And, it requires special knowledge, special expertise to use. It's not usual programming. And why do I build a new programming language to bridge this problem? Because we live in the era, when LLMs are broadly used, and since this progress we have been observing recently, it's quite reasonable to ask whether or not we can use AI and large language models in order to help make up proofs. So in this video, I'm gonna delve into some relatively shallow details of how LLMs operate, into deduction that is used in mathematics to prove theorems, and we can see why LLMs, it's a disclaimer, are not ideal so far. So let's get started. First of all, let's recall how LLMs work. Of course, it's kind of black box, and no one, I think, can for sure explain to the very deep detail about LLMs internals, but in a nutshell, while been talking about LLMs, we need to consider three important things. How LLMs learn, what is a self-attention mechanism, and what is a context window. Speaking about the learning process, it looks like that. We need to prepare a large dataset with labels for each piece of data in order to feed it to LLM. Why we need labels? Because we want an LLM internally makes up patterns that will allow it to recognize and predict the proper answer, which is stated in labels. Then we use human interventions in the process. It's called reinforcement learning with human feedback. And it means human beings sit and compare the answers of LLMs with their perception and their understanding of the proper answer, and give a feedback or binary or scaled whether or not the response is good. This process enables what is called a fine-tune, so a model can be more tuned for a particular task, of course influenced by trainers or people that fine-tune it. So we feed our data to LLM. What happens then? The first phase is a tokenization. What LLM does is it splits income data like text into tokens. Tokens could be words or sequence of several words or punctuations, and then analyze it. This analysis begins with embeddings. Embedding is a process of transforming tokens into multidimensional vector that is easy to work with since LLMs are a big matrix computational mechanism. And then a pattern that is called a transformer or approach of transformer that was invented in 2017 is applied. Well, in a nutshell, what it does is it takes an embedding vector or multidimensional vector and tries to understand it in order to distribute weights among each tokens and find out relations between those tokens. And the larger the embedded vector is, the more resources is required. The complexity is quadratic. So we use transformers to analyze an embedded vector to, make a weight map to know a little bit more about what's inside. And then transformer passes these results to the encoder. This is another layer inside the LLM. The job of encoder is to take information from the transformer and encode it into the rich context-aware representation. It organizes information into layers, it produces a number of identical layers, and then a self-attention mechanism steps in. What happens inside is algorithm calculates three things: the query, the value, and the key. The idea is to calculate weight of each token in the sequence in relations to every other tokens. It's heavy computational process, but the idea is to reveal most reasonable sequences of tokens. And having this, we built what is called an attention window, meaning that since we know the most heavy from the weight perspective vectors of tokens, we can choose to, what's it called, like pay attention to them most and slide our context from less reasonable information. For instance, if it's a token and it's a punctuation, so probably in some cases, punctuation might be less important, the sentence itself with the statement, for instance. So like this process like allows LLM to, get rid of like or exclude from analysis what is less important up to its consideration, of course. Now, what is also important is the context window. We know that our model is good, well educated with human feedback, and also it has this sophisticated mechanism of preparing and using self-aware mechanism and the context. The context is actually like an read access memory, or like what a model knows about what's going on right now. Meaning, if we're talking about the conversation, it keeps everything in its memory. Of course, the representation is tokenized and all this vectorization is happening. But the problem here is that the context is limited. And it means that we cannot continue a conversation in the common sense of the conversation word endlessly. At the moment when the threshold of tokens an LLM can keep in the context window reached, it begins truncated or forget, we can say. Like it cannot recall what was n tokens before because they're just out of the context window boundaries. Now, what it means on practice? Well, if you work on code, you can put it into the context window fully. But if your project is large, it's impossible to keep it in the context window. So, of course, some advanced techniques are being developed, like RAG, when people try to, keep embedding somewhere outside the context window and then embed them, like to take them from the outside and bring into the current context to relax the current context density with something like you don't need to analyze and, refurbish all this data. We can just take them from the outside storage, like a database, and then use it in this context. But it's like a hack more, in my opinion, not the ideal solution. So now we know that the context is limited, context window is limited, and we can use it effectively, like efficient, as long as our data is bounded inside and the context is not being truncated. Otherwise, LLM will not be very helpful because it forgets about what was before. Now, in a nutshell, what is a code correctness? So I use this term in a way of reason or to know something about the code in a formal way, meaning I want to formally or unambiguously know something about code. And it's better not to only know, I just don't want to know, I want to be sure. And the only way to make me, be really sure in something is to represent something I can really trust and rely on. For my perspective, I can rely only math, since it has strict rules that must be respected in order to say that this code is correct or sound, system is sound. When developers write unit tests or use other techniques like fuzzing or mutation tests or any other fuzz tests or uncertain tests, they actually do informal testing. Why? Because they try to offer some pseudorandom or particular input to functions they test and assess the result or the system behavior. It doesn't really matter in details now. What matters is this approach can, prove or make us be relatively sure in what's going on with the system, what happens with the system, and what result it will return as a response on our signal we pass it to. However, it's not formalized, meaning I cannot say this system works like that, because for every input, or if input is like that, then it works like that. I don't have premises and results that rely on these premises. I cannot imply something from the input. I can only, say okay, if I pass A and B, it will return me some C, but it's not a paradigm. It's just a case, an example. So we need to abstract from particular examples to the upper level, and that's why we use automated theorem provers to use math for making up such proofs. Now a little bit about theorem provers. So of course, initially we know that people use pen and paper to write math and write proofs for theorems, as we did it in school or in university. And this approach works fine as long as your proof can be, suited to 3-4 sheets of paper. But if your proof is like a small book, then it's possibly unrealistic that it can be analyzed by people. So automated theorem provers were invented, and in there we write proofs in code, usually in functional way. And we can more or less, of course, rely on the correctness of these provers. So because they were designed by mathematicians and they force you to follow mathematical rules, you cannot tweak it. And these proofs are the same math as you write on the paper. That's why we can rely on them. Internally, they verify that you do not cheat, that you cover all possible cases or destruct all constructors, things like that. That's why we use them. Now, let's think about how people do math. It's my speculation, of course. I think here it works like that. During your education in school, in university, etc., you absorbing knowledge from different subjects, from different classes. And this is how you expand your large context that inactive most of the time. Then when you approach a math problem, as like my experience, you always, begin with struggling. Oh, how to do it? I try to, recall formulas or something like, oh, it could be this or that. And then going on, I'm winning this in my mind like, oh, I could heard it 5 years ago or maybe 10 years ago or something like that. And then this, like how our internal neural network works, we built a long road path to the proper cell with a piece of knowledge we need to extract back and propagate it pop to the actual context, and then we use it and solve the problem. For us it works pretty well. Comparing to LLMs, we have, or at least me, very narrow active context or awareness. Like we can keep in mind very certain small piece of information at the moment. We can, operate with very accurately with small details and analysis. Like if we're talking about text, it's like keeping in mind the sentence or a paragraph. I think this is my maximum. If I began reading the second paragraph, I cannot absolutely reproduce the previous one. With the neural network, it's like opposite. It literally remember everything as long as the context is not full. But the problem is that it cannot bring this like a story that happened a long time ago. I mean, like it needs to find something in the very old, covered with the dust box somewhere, on the warehouse, and it brings into the context information from nearby. To approach mathematical problems, we need to use the largest possible context, and it should comparing to the LLM context that is dense. We're not necessarily into dense context. We need a sparse context, but super large, and this is what LLMs do not have, at least at the moment. So this is the reason why LLMs at the moment cannot be used to prove theorems and build math theories and prove them, but it doesn't mean they're useless. They have several really cool superpowers that are useful and that we use, and I personally use on a daily basis. To begin with, they're very good in reproducing things that other people already done. For instance, they're really good in code generation. For instance, you can say, okay, here's a couple of examples and generate me similar examples, and you can use them as cases to check, or generate me this code or this algorithm. You're not really interested into the implementation details, but you need something like a raw material to work with and to post-process, or to test your environment or behavior, for instance, a compiler. It could be a fuzzer, or they're really good in searching for information, not like self-context enhancement, but with give me this information, or what other people have done with this problem. Can you recognize some patterns from a sequence of tactics that I use? Yes. So these are very good use cases. Now, in regard of the situation, like, okay, you might say, what if in 5 years or in 3 years, in 2 years, doesn't really matter, the problem of the context will be solved? Like if LLM would have an infinite or potentially infinite context window? That's a good question. Here's the problem. When you work with proof assistants, you see the source code, so you know how it works internally, and you can go through the whole code base of all tactics that you used. If you have this challenge in front of your face, you can actually approach and go through each line of code and see and make sure that the proof is prepared correctly and it works correctly. For LLMs, it's not a case. At the moment, LLMs are black boxes. We know how we feed it. We know some algorithms that are being used in the middle, but the model itself, the result, is something unpredictable, uncertain, and my understanding is that now we do not understand how these models, like a multidimensional mechanism, work. Meaning our math that we have now says that, okay, for this situation, certain situation, the results should degrade because of, mistakes that appear in, and results should be worse. But in fact, what we observe, the behavior is different. So some attributes, some qualities inside LLMs appear unpredictably. People, scientists haven't expected that it happens. That, for instance, if you feed a LLM with some information about biology and math, maybe a little bit with chemistry, then you are not expecting it to know something about, let's say, something in the middle, or like how to calculate some formulas for microbiology or something like that. I'm not a chemist, but for a reason it could mine this knowledge itself, and we don't know how. And this is the problem. Even though we would want to rely on the result LLM gives us, we cannot, because we cannot reconstruct it or analyze, as I said, line by line, as it's not a code, it's just a response from this block of metrics and weights, and it gives us in response, and we cannot track how it did, and even though we could, it will give us nothing. So it's something like we cannot rely on for sure. There are some research being conducted this time, like people try to use either symbolic abstractions for tokens and try to track them inside LLMs, like to be more aware of internal structure, how the query goes through matrices. But as far as I know, there's no any luck with this so far, but we will pay attention to it, of course. So to wrap up, LLMs are powerful grinders and digest forges for grounding data, and to query it, we're sophisticated, but we cannot rely on them. So this is the problem we still must address ourselves to be sure. If we work with something mission critical like finance, in blockchain, smart contracts, we must prove properties of code ourselves, or like for aircrafts or spaceships. We cannot rely on things that we do not understand how to work. Here I consider that it has an infinite context window. Like we cannot rely, we have these instruments and we must invest our time, efforts into make them better, to learn them. And this is my mission also. I build Inference programming language for developers, so they can use this math approach that we have been using for thousands of years as humanity, in order to be really sure, not to just rely on something, but trust themselves, yourself, like, yes, if it works, then it works. If proof assistant says that the theorem is really proved, the system is sound, meaning there are no contradictions inside, that it's really ready to go, and people can lock their money into this DeFi protocol or whatever you develop, and they will not be hacked or lost. Thanks for watching. Please follow us on GitHub, leave your comments, and I would like to know what you think about LLMs in the future in such, scientific domain especially. It's really interesting. See you. Bye.